Hey physics students, it's Mr. Scott, your local astronomy and physics teacher, trying to help you guys out with the backside of 3-4, which has to do with air resistance and force of gravity and Newton's second law. The first thing I like to do in any physics problem is always identify the givens. So here, as we've highlighted in green, you've got a mass that's going to be equal to 100 kilograms the entire time of our Elvis skydiver, and then we've also got a constant force of gravity that won't change because, force of gravity is equal to mass times acceleration of surface gravity here on Earth, which then means that it's going to stay the same at 1,000 newtons the entire time. Lastly, since we know that there's only two forces that are going to be acting on our skydiver the entire time, we can take Newton's second law, which is F equals ma, and then expand the left side of the equation to have these two forces for force of gravity and force of air resistance, which we'll call FF, or force of friction, because air resistance is a form of friction, and making sure that one is positive and one is negative. Note that we've already defined that the force of air resistance, which will end up pointing upward, is going to be negative and down is going to be positive. Alright, let's start drawing some free body diagrams and using some net force calculations. So here Elvis is jumping right out of the helicopter, and as you can see in the first position that he has no force of friction, which means that this is an easy free body diagram to draw. We're just going to draw some arrow down at some length and call that the force of gravity, and representing 1,000 newtons of magnitude in the direction down. Next, to save time, I've added in the work that you need to solve for the acceleration that will be acting on Elvis at that spot. So notice here that because you only got one force going down, you have only one force in your net force equation, and then you can set that equal to ma. The mass, as we learned on the last page, is 100 kilograms of Elvis. Divide that to both sides, and like you'd expect, when you have free fall with no extra forces acting on you, your acceleration is 10 meters per second squared down. For the free body diagram in the second position, you'll note now that the force of friction or air resistance is starting to get larger, acting on Elvis. So as he begins to speed up, he's moving more air molecules and they're starting to push back on him a little bit harder. So here we see at this second there's 400 newtons of friction, so we're going to add in an arrow that's just about a little under a half as much as the force of gravity arrow that we defined with the first picture. And kazam, there's the work for the second situation, and notice that we now add in the second force of friction into our net force calculation. We call it negative because it's going the opposite way of the force of gravity, which we're going to define as positive down, and our acceleration ends up being 6 meters per second squared. This should make sense because the net force and the acceleration will always point in the same direction, and it should be a little bit less than what it was in the first place because now the force of friction is acting upward against the force of gravity. Okay, now let's look at the next three positions after those first two, and we're going to draw on the force of gravity again as the same length arrow that hasn't changed since we started. It's still 1,000 newtons, but this time our force of friction is going to have to change depending on the magnitude. And notice that in the last two positions here, 1,200 newtons and 2,000 newtons, it should be longer than the force of gravity arrow because now it's more and our acceleration is going to point upward. Alright, looks good enough, and on a quiz you guys can use a ruler to make sure that your scale drawings are perfectly to scale, not just completely drawn in here by estimate like mine. And let's go ahead and add in the work here for these three that hasn't changed. We're just changing the values of the numbers, but the equation setup stays the same. And as you can see, we've transitioned from our acceleration pointing down to now making it 0 and then even pointing upward, which means that we're slowing down instead of speeding up. When our acceleration was 0, we were staying at a constant velocity. And then here's the work for the last position, and as you can see, we're now coasting down to the ground. The parachute has a force of friction and air resistance that's exactly equal to the force of gravity, and 0 meters per second squared means that the net force must be 0 too. Okay, now let's answer some conceptual questions and see if we actually understand what happens with a skydiver as they go down and a parachute opening up in terms of net force and free body diagrams. So number 7 asks, when Elvis's speed is the least, his acceleration is blank. Well, let's think about this. If you're jumping out of a plane, you're going to be going 0 meters per second, free fall, right when you start, so that's when your speed is the least. When's your acceleration going to be the most? Well, that's also at the same time, because as you can see here from our answers on the previous page, that we have 10 meters per second squared of acceleration in the beginning. We get negative 10 down there, which is the same magnitude, but this question is trying to make you see that by far the highest answer value is when we are going the slowest. So your answer for number 7, most. Number 8 asks, in which positions does Elvis experience a downward acceleration? Since we define down as positive and up as negative, all we have to do here is look for when the acceleration is positive. Note that 0 meters per second squared is neither positive nor negative and is not going to have an upward or downward acceleration. It's just 0. So the answers for 8 are just A and B. Now 9 asks, when do you feel the upward acceleration? So look for when the acceleration is negative, and if we scroll down, we can see that that's going to be positions D and E and nothing else. Number 10 asks you then, when Elvis experienced an upwards acceleration, what's his velocity doing? Well, think about it this way. Velocity is how fast you're going, and does Elvis ever come to a stop and go back upwards when he's skydiving? The answer is no, right? So that means that he has to be having the velocity point downward the entire time, no matter what, okay? And even when you have an acceleration that points upward with the net force at positions D and E, that skydiver is still moving down and still has a velocity that can go against the acceleration. In number 11, it asks, in which position or positions is Elvis's velocity constant? Anytime you see these two words, constant velocity, in this chapter, it's very simple. It means you have no change in v, which means you have no change v over t, or acceleration. And if you have no acceleration, because F equals ma, you must also have no net force. So that's a very important distinction. If you ever see velocity constant or constant velocity, you have to immediately think we're just an object at rest staying at rest, or an object in motion staying in motion with no net force. So for Elvis, this happens at position C and position F, where you have an acceleration of 0 meters per second squared. Number 12 asks about when Elvis is going to experience terminal velocity. If you remember from first unit, terminal means end. So that is the velocity that somebody who's in free fall is going to feel once the air resistance matches the weight. And they will coast at that velocity depending on how much mass they have until they eventually get hit by some other new force or one of the forces goes away. So, in this case, terminal velocity is felt when the force of friction equals the weight, and again, that happens at positions C and F. Question 13 is actually probably the toughest question on here. So now we're really thinking high-level physics. When is the terminal velocity going to be the greatest? So you have to think to yourself, when is Elvis on this fall going to be moving the fastest? Will it be moving the fastest without a parachute, like in position C, or will it be moving the fastest with a parachute on him and opened up, like in position F? So if you know just basic knowledge about anybody who skydives, you're going to be moving faster when you don't have the parachute open and catching as much air. So because of this, we should have the higher terminal velocity when we're at position C. And then the next question, 14, asks you, well, what if Elvis was heavier? What would be happening to his terminal velocity? If that's the case, then he would be able to displace more molecules per unit time, be able to move more of them, have more molecules moving back against him, and it would also need more air resistance to be able to match the excess weight. So because of that, your terminal velocity goes up when you're more massive. Then if you're less massive, it should go down. And here, like I said, we're going the fastest at C, but we still can coast even with that parachute on at F and then land safely at a lower velocity. All right, folks, that's it for me. Hopefully you learned something with this practice file. And yeah, if not, go talk to somebody. We're here to help. Bye.